FCC catalysts are microsphere particles with an average diameter of around 75 microns. The KNT group manufactures advanced catalysts with exceptional physical properties such as particle size distribution, attrition resistance, density, and an ideal spherical shape. This ensures our catalysts provide excellent catalyst fluidization in the units for stable operation at high throughput with minimum losses. The main components of the fluid catalytic cracking catalysts are zeolite, matrix, and binder. Zeolite is the key and most expensive component of the FCC catalyst. It exerts the main effect on the catalyst activity and thermostability, and accordingly on product yield and selectivity. Modern catalytic cracking catalysts use synthetically produced forgasite-type zeolite Y. Zeolites are crystalline silica aluminates. The basic crystal structure is tetrahedral, with a silicon or aluminium atom in the center of the tetrahedron and oxygen atoms at the corners. These basic building blocks combine at their oxygen atoms to form a cell structure with well-defined pores and a specific diameter. This elementary cell has 8 supercavities. The unit cell size is the distance between repeating cells in the zeolite structure. The selectivity and yield of the catalytic cracking products will differ depending on the unit cell size. Initially, the structure of zeolite Y has an entrance window with a diameter of about 8 to 9 angstroms. For that reason, it's virtually impossible to perform the cracking of hydrocarbon molecules with a diameter of more than 9 angstroms and a boiling point above 480 degrees centigrade inside the zeolite cells. The special processing technology applied by KNT Group makes it possible to produce zeolite Y with secondary pores of 3 to 4 nanometers in diameter. These pores are covered with an active aluminosilicate phase from the inside. Thus, distinctive nanoreactors are formed inside the crystal, in which cracking begins in secondary pores and continues inside the zeolite. The silicon atoms inside the zeolites are electrically neutral, while the aluminium atoms carry a negative charge and form an acid site that enables the catalytic activity of the zeolite. The key parameter of the zeolite is the unit cell size, the length of the smallest repeating unit in the crystal. The aluminium-oxygen bond is longer than the silicon-oxygen one. Therefore, if the number of aluminium atoms in the crystal increases, the unit cell size is greater and indicates a higher activity. The zeolite unit cell size is controlled by the rare earth element content in the zeolite. The presence of rare earth elements in the acid sites stabilizes the aluminium atoms in the crystal structure and prevents aluminium withdrawal from the zeolite framework during high-temperature exposure in the FCC unit regenerator. On the other hand, unit cell size enhancement indicates that aluminium atoms or acid sites are located closer together, which leads to an increase in hydrogen transfer reactions that results in both lower olefins content and the gasoline octane number. Thus, increasing the rare earth elements content level in the zeolite cell enhances gasoline yield while reducing its octane numbers and vice versa. The KNT group has developed superior zeolite Y with high resistance to thermal deactivation, i.e. the retention of a specific surface area and activity relative to the initial values, which is reflected in an increase in the specific surface area of the equilibrium catalyst when loading a fresh KNT group catalyst into the FCC unit. Matrix is another important component of the catalyst that acts to bind particles together to provide the catalyst with its physical properties such as hardness, density, and size. In addition to acting as a binder, some types of matrix alumina enable important catalytic activity. Active forms of alumina provide the catalyst with additional active sites within a pore structure that is readily accessible to large molecules and thus enhance the cracking of heavy oil fractions to minimize bottoms yield. The size of heavy hydrocarbon molecules is 30 to 50 angstroms. Therefore, the active sites of the zeolite cell are not accessible for cracking. Matrix with an optimal mesoporous structure allows for both the preliminary cracking of molecules with a high molecular weight to a smaller size, and the diffusion of feed molecules to the zeolite active sites, which increases the cracking efficiency of the bottom feed. The optimal pore distribution provides for not only high conversion, but also more efficient product stripping from the catalyst pores. The KNT Group's novel matrix technology provides a controlled matrix pore structure and acidity, acid site type, strength and density, and as a result it is used to vary the catalyst coke selectivity across a wide range, from minimum delta coke to process heavy feedstocks to maximum coke selectivity to convert low con-carbon feeds. The synergistic effect is the result of using superior zeolite technology together with active matrix, where the activity achieved by their combined action is higher than the sum of their individual activities. Such interaction can be represented in the form of a three-stage reactor, where hydrocarbons with different molecular weights are cracked at each stage. The use of heavy oil residues as feed means that they contain heavy metals, catalytic poisons such as nickel and vanadium. Nickel deposited on the matrix surface promotes dehydrogenation reactions and increases the yield of dry gas and coke. Vanadium present in the FCC feed damages catalyst activity because this metal easily migrates through the catalyst, reacts with the zeolite, and destroys the crystal structure. This leads to an irreversible loss of catalyst activity and surface area. KNT Group's proprietary metal trapping technologies are used to control vanadium mobility and prevent loss of activity, and to passivate nickel to reduce the hydrogen yield. For example, one type of nickel trap is based on the interaction of active alumina with nickel forming spinel, which is inert.